Hello, everyone. Thank you for joining us, and welcome to this webinar, part of the DataGEMS project funded by the EU. Today, we will be talking about data discovery, a very interesting and challenging problem with many facets, as we will see, many different ways that data discovery is used and affects research, but also has many applications that, as we would see, uh, we interact with data discovery systems more than we might think. But first of all, let's talk about what is data discovery and why it is important, especially today, where data is being generated at explosive rates. And an increasing number of human activities are fueled by data, and people use data to make very important decisions. In fact, in many different areas, such as government and policymakers use data to take the right decisions for the people. Agriculture uses data to make decisions on the right way to move forward. And the same goes to medicine, healthcare, but also businesses of many different sizes nowadays make their decision based on data to make the most out of what they have. And what is interesting is that it is estimated that about 400 million terabytes of data is generated every single day, which is a number that is difficult to fathom. So you can understand that a lot of time and effort is lost by searching for the right data, the right data sets to use for many different purposes, as we said. And in fact, a lot of data is being lost because of the sheer amount of data that is available. So sometimes people might make decisions on a certain set of data, but in fact, there were better data that they could have used for what they wanted to do. So I think we can agree that finding the right data at the right time can make a huge difference in all these different sectors. And when we talk about data discovery, it might sound like a simple term, but in fact, it hides many different facets and many different things that are actually data discovery. So, for example, if the user is asking a question and they're expecting an answer, this is a research area that is often called question answering. So what we have to do is we have to consider what kind of data can answer that question, find the right data, and use that to answer the user's questions. And we will see some examples in the next slide. But what I want to say here is that there are many different research areas on question answering based on the underlying data. So right from the start, we have three different research areas that are actually data discovery. Another research topic that falls under this umbrella is the case where the user already has some data and they want to find additional data that can be combined with what they have and discover more synergies and increase the value of what they have. This is the research area called union discovery and joint discovery. So we're looking for new tables that we can combine with what we already have. Two other interesting research areas are table retrieval and dataset search. And in these cases, we have a user that wants to find a specific table or a set of tables or an entire data set. And I think you get the idea that we could go on, and there are many different facets, as I like to say, of data discovery. And I think it is easier to understand this with a few examples. So to make these examples make sense, I will show you a quick categorization of different types of data discovery and what we need to consider. The first axis is what is given by the user. So the user input type. How does the user express their request or their need for data? They can give a set of keywords like, let's say, movies, restaurants, and so on. They can express their needs through a natural language question, which is beyond just keywords. They make a full sentence. So, for example, I want to know what the weather was in Athens when the last Olympics started. The user can also give, like we said earlier, table. It's a interface where they can specify their needs. And then another thing is, what does the user expect as a result? So what are they looking and what would they like to see as an answer from our system? Do they just want an answer? So if they're looking for the temperature in Athens, it's just a number. Are they looking for an entire data set that can contain many different files of different types? Are they looking for a table or a list? So they could say, I'm looking for restaurants, and they expect a list of restaurants, and so on. And another important aspect is, what do we use to verify that the answer is actually matching the question? So what are the properties of the answer? Do we care about similarity? So when the user says restaurants, we want things that look like restaurants. When we're looking for answer, we are concerned about answerability, so that the returned output answers the input. Joinability and unionability when we're looking to combine datasets, and so on. And let's see some examples to make this clearer. So one input could be Italian restaurants Athens. This is a set of keywords because it is very short, a few words. It's not a full natural question, but it's still understandable that the user is looking for a list of restaurants, and what they care about is similarity, that the results are similar to the keywords that they gave. As I said earlier, the example of the last Olympic that took place in Athens, here the user is giving a full natural language question. It's a natural sentence, as we would communicate between humans. And they are expecting an answer. So here the answer would be just a date, the year, or even the specific day that the Olympics started. And the property of the answer is that of answerability. So it is the correct answer for this question. Another interesting example is, let's imagine a data scientist that is trying to create an image classifier, and they express their need in natural language, saying that I am looking for data sets to train an image classifier. In this case, the answer will be a data set. In this specific example, a data set of images and their labels. And the relevance criteria of this data set is that it can be used for the specific task that the user is specifying. So it is a task-oriented dataset discovery request. And as you see, besides the many facets that this problem has, there are also many challenges that a researcher or a software developer must take into account when building such a system. The first one is understanding and adapting to the user question, because as we saw, the user can ask many different things, and each of these cases might need completely different handling, might need completely different technologies and approaches. So we have to look at what the user is asking and not move blindly, and understand if our system can handle this, and if it can, decide the right path to complete this request. Another challenge is handling very large amounts of data. As we saw, new data is being generated daily with explosive rates. So our system must be able to handle very large amounts of data in an effective manner. So we must consider our storage requirements. It must not take that much, so it can be handled by our infrastructure. And we must also be able to perform search and return the results in a timely manner, because the user is not going to wait forever for this request. Otherwise, they will leave our system. Additionally, another challenge is integrating new datasets seamlessly, because like we said, new datasets are being generated, but our system cannot shut down, ingest new data, and then come back up. It must be constantly online and serve requests, but also ingest new datasets at the same time. And like I said, we must return the answer within a reasonable amount of time to actually be useful and meaningful for the user to have to use our system. And so the question that follows is, how can we design a system that tackles all these challenges? And as we will see, more challenges will arise. And what is the architecture of such a system? So as we move on, I would like to show you a more, let's say, generic architecture of a data discovery system. And we will go through each part of the system separately and explain it. But just to have a quick overview here, on the top part of this figure, you can see the offline phase. So this can happen before our system starts to serve requests. Usually we have a corpus of data or data sets that is given, and we say that our system must work over this data. And new data might come as time goes on, but at least as a starting point, we have to profile and pre-process all this data that might be of different types, so that everything can be used and be searchable from our system. And then what happens is that we create an index, which is a data structure that helps our system tackle all the challenges that we mentioned and perform searches efficiently and in a timely manner. And then we have the online phase, where the system is available to the user to answer their questions. And when a question comes, usually the first thing that happens, but not always, is understanding and processing the system. Like I said, we have to figure out what the user is looking for and plan our actions and how we're going to answer their request. And then we actually start searching using our index that we mentioned was created in the offline phase. And this search, because the data that is available will be usually very large, must happen very fast, because we're searching over a huge amount of data. And then we get the preliminary results, as we like to say. Usually what happens is a two-stage search process, a coarse-grained search, and then a fine-grained search. So this first part gives us some preliminary results. And then what happens usually is that we re-rank these results. So now that we have a smaller set of candidates, let's say, preliminary results, we can use a more expensive but more accurate searching technique to re-rank these results and finally give the user a list of what we think matches what they asked for. But we will see all these steps in more detail. So we start with the offline phase, and the first step, like I said, is profiling and pre-processing the data that our system will serve to the users. And the goals of this component is, first of all, to understand the data that was given to us, which is not always very easy, because usually online we will find dirty data that doesn't have a lot of documentation. The file types might not be present or might not be very helpful. And they can take many different forms and not always follow the same standard or the widely accepted standard. Then we must look into these files and identify what is actually useful and extract this information and decide what we're going to use from each data file and each table and so on. And sometimes we might even want to create additional information that will be helpful for discovery later on. So to see some examples of what can happen in this step, for example, we could use a large language model and ask the model to generate an explanation of the table, because we can imagine that we might have a very large table with many rows, and it might not be useful to store all these rows in our index. So it might be preferable for the LLM to generate an explanation, and we just keep this explanation, which has more information and more useful information to serve search requests. Or similarly, with a very large document, we might just want to generate a summary of this document that will be equally useful, but will take much less space in our index. Or similarly, we might want to, when we have a very large table, we might not want to store all its rows or all its columns, which might have a lot of repetition and might not be very useful for what we want to do. And finally, we might encounter files that have missing file extensions and it might not be clear what is the right way to use them. So in this case, we might use an LLM or another neural network to understand what the contents of a file are and how we can add it to our index. So when we have finished this pre-processing of the data, we want to store it in our index. And what happens in this case is that we want to create representations of the data because it would not be efficient to store everything. It would firstly take a lot of space, but it would also not be useful for searching. So we want to create representations or vectors of the processed data and save them in our index so that we can search through them fast. But there's also things that we have to consider here, like deciding on the level of granularity. And what this means is that, for example, when we have a table, do we want to create a representation, a vector that corresponds to the entire table? Do we want to create a vector that corresponds to each cell separately, to each row, to each column? And there are, in fact, many different ways we can approach this without having an answer that is correct all of the time. It depends on the use case. But this is also something that affects how much storage we're going to need to store all these vectors, and also how accurate our system will be. Because if we have fine-grained representations, it will be easier to find smaller parts of the table, and when we have a representation of an entire table, we might lose some information that would be useful later on. And another big decision that we have to make when creating the index is what types of vectors do we want to use to represent all the data? So for example, we might want to use sparse vectors that match specific text. So if the user asks something the exact way it is stored in the data, it would be easier to find it. Or do we want to use dense vectors from a neural model that help us perform semantic matching, which means if the user says something, but it is stored in a slightly different phrasing in our index, it will still be able to find it, but it does not guarantee that we will find the exact word all the time. And then we move to the online phase of our architecture, where the user gives us a question, and we want to find the right data. And then the first step here is understanding and processing the user's question before starting to search. We have to decide on the appropriate workflow based on what the user is asking. And we also want to consider that the user's question might be ambiguous, and it might not be clear what they're asking, or they might not even be aware of what our system can actually do and ask for something that we cannot answer, or we don't have the right data to answer this. So in this step, some common things that happen is we might use a classifier, it may be traditional machine learning or neural network or a language model to read the question that is given by the user and decide what to do. We might have to identify the ambiguity and ask the user what do they mean when they ask this, or maybe they want to rephrase their question and ask for something else that we can actually answer. Or another interesting thing that we can do is we might want to discover specific parts of the question that we believe are more important. So we put emphasis on them when we actually search our index. And so when that is done, we move to actually searching in our index. And like I said, this step aims to find relevant data from all the data we have available, but we want to do this quickly and efficiently because the size would be very large. So we need an approach that would be computationally cheap, and this is handled by an index like the ones we described, because we want to be as fast as possible and make sure that in this step, relevant data is not missed. It's okay if we don't rank the best results higher. We just want to have a high recall here so we don't miss anything, because as I said, we have re-ranking as a next step, which will take care of the right ranking. So we use efficient algorithms to avoid unnecessary computations, but also take advantage of the index structure to ensure that relevant data is not missed. And then finally, we want to re-rank all these preliminary results because we consider that the answer is in these preliminary results. It might not be on the top of our answer. It might be in the middle or very low, but that is okay. Because in this step, we have the advantage that we don't need to consider all our data. We just need to consider these preliminary results, and we can use more accurate and more expensive from a computational aspect algorithms to filter out results that are actually not relevant and to make sure that the most relevant are first in our ranking. So some extra things that we can do in this step is that we can actually look into these preliminary results. We don't need to just look at the representation like we did earlier. We can go into the data and make better comparisons, and we can take advantage of models like neural networks and LLMs, which are more expensive, but at this point, it doesn't matter because we're dealing with smaller amount of data. And so this is the architecture that we discussed. We can see again that this online process is separated in two different searches. And this, like I said, is because we want to balance two things, which is one of the big challenges in data retrieval. We want to balance recall and precision. So the coarse-grained search guarantees high recall. So we just want to make sure that we don't miss something that would be interesting or would be useful for the user. And then the fine-grained part of this search focuses on having better precision and making sure that now that we have managed to find the right data, we rank it higher in our list so that the user sees in the first results what they actually need, and they don't have to look through a big list and lose a lot of time filtering out things that they don't actually need. Okay, now that we have an idea of how data discovery systems are structured and what their architecture is, I would like to show you some applications, some examples of how data discovery systems are used and how they can be applied to make interesting use cases and applications. Another thing that I want to mention is that before going into this specific example is that data discovery systems we can also consider search websites like Google as a data discovery system. And as we will see in this example, even ChatGPT and systems like that have data discovery integrated inside them. So they're not they're more ubiquitous than we might think, and we use them a lot in our day-to-day, even if we are not data scientists and so on. So first of all, I want to talk about the RAG pipeline that you might be familiar with. This was made very famous because of LLMs. And the problem that LLMs had that because their machine learning models, they often hallucinate. And when we ask a question and they don't know exactly the answer, they might give results that are not correct, but they look correct because that's what they have been trained to do. So to tackle this challenge, scientists proposed retrieval augmented generation, a framework that makes LLMs respond using specific data sources. So to start to build this pipeline, we decide that we want our model to work over a specific set of data. And I have an example here. So let's imagine we have a company and there is a business analyst in this company. And this business analyst has a specific a pool of data that is about clients. So we can imagine this could be contracts, this could be sales, this could be reports of what was transferred to each client and so on. And what this analyst does is that they have a question, they want the system to prepare a report about their clients. So the LLM will handle this report, but the interesting part is that for the LLM to do a good job, it must use the most relevant data and the data that actually includes all the information that is necessary to produce the correct report. So this is where data retrieval comes into play. And essentially what happens in this component is that, first of all, the data retrieval component must look at all the client data that was given to it by the analyst. It will create an index internally so that when the question comes, it will quickly search over this data and find, for example, which are the clients in Southern Europe and what type of information is needed from these clients to produce a report. So this includes understanding the user's question and understanding what the answer will look like and what data is needed to answer it. And then the index will perform a quick search and return the most relevant data. And then this data can be passed to the LLM, and the LLM will use this very specific data to produce a more contextualized answer and hopefully avoid hallucinations and problems that might occur. And like I said earlier, something similar also happens with commercial LLMs like ChatGPT. So nowadays, it's you might see when you ask a question, the model will say, "I'm searching for relevant data" or something similar. And in some applications, you can even see which websites or which data was found to produce a more specific and a more contextualized answer to your question. And this way, the LLM doesn't have to think on its own and hallucinate and cause problems like that. Another application I wanted to show you is dataset search. This is something we're building for our component in DataGEMS. And we saw a similar example earlier. So in this case, imagine that we have a data scientist, and they have a specific project, a specific application that they're building, and they want to train a machine learning model, whether that is deep learning, language model, it doesn't matter. Finding the right data set is very important for data scientists. And some studies show that data scientists spend more than half their time looking at data, finding the right data, and processing this data. So this application, the user can express what requirements they have for their data sets. So for example, this data scientist wants to find sports data sets. They want to use them for a specific task that is sentiment analysis, and they also care that a specific player appears in these datasets, maybe because the project that they have is with a specific team or with a specific player and so on. So this application that we're building allows the user to express all their needs in natural language, which basically avoids having hard to use interfaces or having the user write complex queries or programs and so on. And the system reads this question, it handles the understanding part and the requirement extraction. So you can see this example, we have requirements about the topic, specific entity, which is this player, and the task that they want to perform. And on the offline phase, what we do is that for each dataset that is given to us, we perform some profiling. And what this means is that we read each dataset and we try to understand what is inside, which again might we might need to do some understanding and some cleaning, like we mentioned earlier. And basically, we extract from each dataset the topics that it mentions. So it might be a medical dataset, it might be about movies, it might be about agriculture, and so on. We extract the named entities that appear in each dataset, and we also try to understand what tasks can be performed with each dataset. And to do that, we might need to consider the file types that it has. So it might have pictures, so it can be used for image classification. It might have information about measurements in different times. So this could be used for time series analysis and so on. And then we create 3 different indexes for each of these requirements that we want to satisfy. So when the search time comes, we have extracted these requirements and we can search each requirement in its dedicated index. And by doing this, we can guarantee that the datasets that we return will satisfy all the needs that the user has specified, and they can go on and do their job exactly as they intended. So another difference to previous applications is that here we don't want just to have datasets that are similar to the question. We want something very specific and something more strict so that the user can do their job efficiently. And then finally, I want to present a pilot that we're building in DataGEMS for language research in collaboration with the German the Institute for German Language in Mannheim, and our colleagues in Zurich, the University of Applied Science. And in this case, we imagine that we have a linguist, a researcher who wants to perform an analysis on different texts. So the data that is handled by our data discovery system in this case is many different text corpora, which means that we have encyclopedias like Wikipedia, but also older encyclopedias that have been saved digitally, like the Diderot encyclopedia, which is in French. We also have German. So this use case must be able to handle different languages as well. And what we do here is that, again, we create an index out of these text corpora so that we can search efficiently. And when the question comes, we do basically three things, as you can see on the top right of the image. First, we want to understand what the user is searching for. So there are two parts in the question that the user gives us. They care about references to T, so they want to find texts that talk about T, and they also specify some constraints. So in this case, they're interested in texts that were written during the 19th century. And in this pilot, they can also specify different things like the language that the text is written in, or, for example, who wrote this and the publisher and so on. But we separate these two different things because on the one hand, the constraints are things that we need to filter. So if a data set or a text passage is not from the 19th century, we do not have to consider this at all. We only want to consider passages that satisfy these constraints. And we use the criteria, which is references of T, to search. And in this case, what we care about is similarity and also specific mentions of the word T. So this is document retrieval. We find the texts that satisfy these criteria and constraints, and then we have filtering. And this is similar to what we talked about earlier about the two-stage searching approach. That the first part finds documents that satisfy this request, but might not be exactly what the user is looking for. So then we have filtering, which can actually take a better look at what we retrieved and consider what the user is looking for, in this case, references to T, and make sure that all the text that we retrieve actually match this request. And then in this pilot, the linguist is interested in extracting specific linguistic features from this text. So, for example, we might want to extract the sentiment. Did this text during the 19th century talk about T positively, negatively, and so on? They want to know about term frequencies, so which words appear more frequently and which less frequently, and collocations between words. So it might be interesting to discover that two words appear very often together. And so this data discovery application saves the user a lot of time from, first of all, searching and finding the data that matches their needs, but also from writing code and processing all this text manually, because it can all happen in this application. Okay, so to conclude, we saw an introduction, let's say, and an overview of what data discovery is and why it is important. I believe that some takeaways that we should keep in mind is that because there is so much data out there, and because data keeps being generated with explosive rates, it is very hard to find the right data for our needs. So data discovery systems help people make the best out of what is out there, because it might be critical in some cases to find the latest data and find it at the right time, because if some time passes, then it stops being useful. And if this does not happen, we actually might miss valuable data that was created, and it might never be used at all. And like we saw, there is a large amount of work that is happening, but there are still many challenges that are not solved entirely. So there is still a lot of work in this area. And finally, to wrap this up, there are related topics and works that I have been involved with. If you found this interesting, that you can take a look at or even contact me. There are related areas like natural language interfaces for databases. So in this case, we consider that, okay, we found the data that we need. Maybe it is a database. How do we use this effectively, and how do we allow people that might not be familiar with database to use them? So this research area looks into how users can use natural language to interact with databases. And more specifically, the text SQL research area, which we have some works on, considers how to translate a question, a natural language question, into an SQL query that can be run over a database to retrieve the result that the user is looking for. So what I want to say based on this is that data discovery, as we saw, is important, but then when the user gets this data, our job is not done as researchers and as software developers. We also want to help the user effectively use this data for what they need, sometimes without having technical knowledge, because data should not only be available for the experts, because everyone can benefit from data. It should be available to everyone. So with this, this concludes this webinar. Thank you very much for your attention.